You're an astronaut. You're really excited about your upcoming trip to another planet, sometime in the not-too-distant future, but there is one thing that concerns you. What if when you reach the planet, you land only to discover that the gravitational acceleration near the planet is much too large for you to survive? That's a real concern for an astronaut. Fortunately, we can do a calculation in advance to put this astronaut's mind at ease. So imagine that we're told that the planet's mass is 5 times that of Earth, and the planet's radius is 3 times that of Earth, so it is both larger and more massive. We know the law of universal gravitation, namely that the force of gravity, at least its magnitude, is g m1 m2 divided by r squared, where g is just a constant. The first step in solving a problem like this should be to write out those statements that I've put in words in equation form. So if the planet's mass is 5 times that of Earth, then if we call the planet's mass m sub p, we would say that m sub p is 5 m sub e, where m sub e is the mass of Earth. Similarly for the radius, the planet's radius r sub p is 3 r sub e. It seems like a silly step. Of course, the words mean exactly the same things as those equations, but ultimately, if you set up the equations cleanly at the beginning, you won't have any trouble later on when we do the calculation. So let's clear out the image and begin. Let's start with the law of universal gravitation, and we need to decide which object corresponds to m1 and which corresponds to m2. I'm going to choose m1 to be the mass of the astronaut. So if that's true, if we want to write down the force acting on the astronaut, namely the gravitational force of the planet acting on the astronaut, I'll label that F1, and from Newton's second law of motion, F1 should be m1 times a1, where a1 would be the acceleration of the astronaut if they were near, but not quite to, the surface of the planet. Okay, well if that's true, we can say that m1a1 must be equal to g m1 m2 divided by r squared. So we can cancel out the m1s. The mass of the astronaut doesn't matter, and of course that's true on Earth. Remember, objects accelerate at the same rate near Earth regardless of their mass. That's true on another planet too. So now we'll see that m2 has to be the mass of the planet. And in this case, let's write out the expression for Earth first. So what is the acceleration of the astronaut if they're near the surface of Earth? Well, it should just be g times the mass of Earth divided by the radius of Earth squared, right? Because their distance from the center of Earth is approximately the radius of the Earth. Now, the same expression for the other planet is that a1p, the acceleration of that astronaut near the planet, is gmp divided by rp squared. So we have two equations, one for the acceleration of an astronaut near Earth, one for the acceleration of an astronaut near this other planet. Okay? We can take a ratio of these two expressions, and explicitly, I'm going to take a ratio of a1p to a1e. If I do that, the left-hand side is literally just a1p divided by a1e, and the right-hand side will be the ratio of the right-hand sides of those two equations. Now you have to be careful here. We have nested fractions, and you have to remember how these work. So if we simplify this, certainly we can cancel out big G, the gravitational constant. That's in the numerator and denominator, so that goes away. The remaining terms, however, become mp divided by me, the ratio of the two masses, times re squared divided by rp squared. And that's often where students make mistakes in problems like this. Since they're inverse square laws, the nested fraction means that re squared goes to the numerator, rp squared goes to the denominator. You have to be careful when doing these. We can move the square outside the parentheses surrounding the ratio of the radii, so we do that. And now we just need to plug in values. Well, where do we get the values? We have expressions over to the left that we set up very carefully at the beginning. mp divided by me, that must be 5, because that top equation on the left says that mp equals 5me. So if you divide both sides of that by me, you get mp divided by me equals 5. Okay, we'll put in 5. Now I also said that re divided by rp is 1/3. You have to be a bit careful. So if you solve for re divided by rp using that second equation on the left, you get that it's 1/3. It's not 3, it's 1/3, and that'll end up getting squared. So now we can do some pretty easy math. The ratio of the acceleration near the planet to the acceleration near Earth is 5/9. Already that's good news for the astronaut. That means that it's smaller on this planet than it is on Earth, so they shouldn't get crushed. Specifically, we can figure out what it is in meters per second squared because we know that the acceleration of an astronaut near Earth would just be 9.8 meters per second squared, right? If they're near the surface of Earth, it's 9.8. So we plug in that value and find that the acceleration of this astronaut near this other mystery planet is 5.4 meters per second squared. The advantage of doing problems this way is that you don't have to track all of these really big numbers using scientific notation. Although I made up the parameters for this mystery planet, any planet that you're dealing with is going to have a really large mass and a really large radius, meaning that it will be times 10 to some big number. When we take ratios, instead of putting in values in kilograms and meters, then you can see that all the numbers we're dealing with are of order unity. So at least that's not a possible source of error in your calculations.